We'll can continue with the basics of software engineering that we have started. And in last session, we have learned almost all the software development model except say agile methodology. So we'll take that one is all that is very important. I'm making a note for comprehensive good notes for uh, agile methodology. So we will continue with uh, prescribed syllabus of software engineering. So next one, software design, where till now we have learned about software requirement elicitation, how requirements can be gathered and how it can be analyzed, and then filing, documenting the requirements in software requirement specification, and we have seen characteristics and the properties of SRS document. Then we can move into the actual step, which in software engineering, which is design. Software design. The first process to transform requirements into some suitable forms, which helps the programmer in software coding and implementation, such as diagrams like DFT, integration, class diagrams, UML diagrams, then like tables in the form of tables, also tree-like structure, and then in the form of pseudocode. So we have the formats that is suitable and that is easier for the programmers to understand the requirements in the design. Okay, so this is the first step in software development life cycle, which moves the concentration from problem domain to solution domain. We have three levels of design: architectural design, which is the highest abstract version of the system, such as like black box. Okay, we are not going to get into the details of how it is implemented, versions of components have been used, technology, whether it is built on stack, queue, data structures, analysis, algorithms. We are not going to care about that. It is the highest abstract version of the system. It identifies software as a single system with many components interacting with each other. At this level, the designers get the idea of proposed solution domain. Next, lower level, high level design. From architectural as a single component to single entity to multiple component. Into concept of architectural design into less abstracted view of subsystems and modules and depicts their interaction with others. Here in this design focus on how the system along with all the components can be implemented in the form of modules, decomposition. It recognizes modular structure of each subsystem and the relation among each other. And then detailed system. Such detailed designs are just EFD or UML. Detailed design deals with implementation part of what is seen as a system and its subsystem in previous two designs. It is more detailed towards modules and their implementation. It defines logical structure of each module and their interfaces to communicate with each other module. So in abstraction level, in the form of abstraction level, architectural design, and then high level design, and then detailed design. Then modularization, just such modules. What we do is divide the problem into components such as modules. And then these individual modules carrying out tasks independently. These modules work as a basic construct of the entire software. Then modular design unintentionally follows the rule of divide and conquer problem solving strategy because there are many other benefits attached with the modular design. Advantages includes smaller components are easier to maintain. Program can be divided based on functional aspects. Desired level of abstraction can be brought in the program. Components with a high cohesion, that is intra-dependability. Intra-dependability. How a module is working as a single unit without interacting or without dependent on other. Components with high cohesion can be reused again. Concurrent execution can be made possible, desired from security aspect. Then what is concurrency? That programs, what we do is we divide we divide entire software into components. Now components are dependent on each other. Components are dependent on each other from parameter passing. Like if we have login modules, a logout module is needed. So those modules, from login modules, we have to pass the information from one module to another module, either to piece or session like that. So modules is working as a single unit, and then modules were interacting with each other. So concurrency is needed. Then here we have two techniques to rate the interdependability and intradependability. Here cohesion means intradependability, which means that how much a system interact with oneself, how it acts as a single unit. Okay, so we need high level of cohesion. And then coupling, interdependability, interdependability, one of the important concepts. Coupling, interdependability, which means modules communicating with each other. Okay, we need low level of coupling. So high cohesion, so a better component. If there is a module and if we say that it can be reused again, that module should have high cohesion and then low coupling. Okay. Now we will see what are the types of cohesion and type of coupling and order of cohesion and order of coupling required. Okay. Then cohesion is a measure that defines degree of intradependability within the elements of a module. The greater the cohesion, the better the program design. Now types, there are 7 types of cohesion. We have arranged in the form of low level cohesion to high level cohesion. So if the first one is low level and last one is highest level of cohesion that are required. In coincidental cohesion, the design is planned, unplanned, and random cohesion, which means that just for the sake of modularization, we break the program into smaller modules. Because it is unplanned, it may serve confusion to the programmer and is generally not accepted. So lowest level of cohesion is coincidental cohesion. And then logical cohesion. Logically categorized elements are put together into a module called logical cohesion. Then temporal cohesion. Elements of a module are organized such that they are processed at similar point in time. Called temporal cohesion. Then procedural cohesion. When elements of module are grouped together, which are executed sequentially in order to perform a task, it is called procedural cohesion. Communication cohesion, again, it is executed sequentially and work on same data, is called communication cohesion. Sequential cohesion, which means that one output is given as an input to other module. Sequential cohesion, elements of modules are grouped because the output of one element serves as input to another element, called sequential cohesion. This is the highly functional cohesion is the highly expected cohesion. It is considered to be highest degree of cohesion and it is highly expected. Elements of module in functional cohesion are grouped because they all contribute to a single well-defined function. It can be reused. So functional cohesion is the highest level of cohesion which is expected, and then coincident cohesion is the least level of cohesion that's not needed. And then coupling, interdependability. Coupling is a measure that defines the level of interdependability among modules of a program. It tells what level the modules interface and interact with each other. The lower the coupling, better the program. We have 5 levels of coupling ordered from lowest level of coupling to highest level of coupling. Content coupling, which means one module can directly access or modify or refer to content of another module. It's called content level coupling. Common coupling means modules have read and write access to same global data. It's called common or global coupling. Control coupling. Two modules are called control coupled if one of them decides the function of other module or changes the flow of its execution. It means one controls another. Stamp coupling, it shares common data structure and work on different parts of it. Here, in common coupling, uh, multiple modules access same global data. In stamp coupling, multiple modules share common data structure, not global data, but data structure and work on different part of it. It's called stamp coupling. Data coupling means when two modules interact with each other by means of passing the data, such as parameter passing. Like we have call by value and call by reference methods. If a module passes data structure as a parameter, then the receiving module should use all of its components. So content coupling is the least expected coupling, and no, see here means ideally no coupling is considered as the best, but data coupling is preferred. Okay. Design verification, how we can verify the design. Here, the output of a software design process is design documentation, pseudocodes, detailed logic diagram, process diagram, and detailed description of all functions or non-functional network. Here, the next phase, implementation phase, depends on all the outputs of the mentioned this diagrams. It then becomes necessary to verify the output before proceeding the next. The early any mistake is detected, the better is not to be detected until testing is okay. Uh, by structured verification approach, reviewers can detect defects that might be caused by overlooking some condition. A good design review is important for software design accuracy and quality. There are two approaches for software designing: top-down and bottom-up approaches. Here, from the top-down design, we we start with components from the top level and go with the specific levels. Here, a system is composed of more than one subsystem and it contains number of components. These subsystems and components may have their own set of subsystem and components and create hierarchical structure. Top-down design takes the whole software system as one entity and decomposes it. To achieve more than one subsystem or component based on some characteristics, each subsystem or component is then treated as a system and decomposed further. This process keeps on until the lowest level of system in the hierarchy is achieved. Okay, top-down design is more suitable when the software solution needs to be designed from scratch and specific details are unknown. So top-down design is suitable for software solution needs to be designed from scratch. Even if we don't have any component, then we can start from top to bottom approach. And then bottom up design, we start with basic components and go with the data and go with the bigger picture. It proceed with composing higher level of components by using basic or low level components. It keeps creating higher level components until the desired system is not evolved as one single component. With each higher level, amount of abstraction is increased. Bottom up strategy is suitable when a system needs to be created from some existing system where the basic primitives can be used in newer systems. Both bottom-up and top-down approaches are not practical individually. Instead, a good combination of both can be used. So, in bottom-up, top-down design is suitable for a software that start with something from the beginning. If there is no component, then we can start from the scratch. And then specific details are unknown. Bottom-up design is preferable when we have some components from existing system. Okay. Then coding part. In coding part, we have some standards and guidelines to be followed. Here, coding style. Advantages of adhering to a standard coding style includes coding standard uniform appearance to the code written by different engineers. It facilitates code of understanding, more good programming practices. Characters of programming language include readability. What programming language that we have used? Because we have seen that SQL is the highest Gen 4, sorry, fourth generation language. SQL, we have seen that SQL is a fourth generation language because it is closely compared with human language. Okay, human language. In terms of readability, okay, a good high-level language will allow programs to be written in some ways that reassemble a quiet English description of the underlying algorithm. And then portability, meaning that essentially machine independent should be able to develop portable software such as Java. Instead of C or C++, we can use Java for cross-platform development. So portability. And then generality. Okay. Which most high-level languages allow the writing of a wide variety of programs, thus relieving the program of the need to become expert in many diverse languages such as Python, JavaScript. And then brevity. Okay. Language should have the ability to implement the algorithm with less amount of code. Okay. Programs expressed in high-level languages are often considerably shorter than lower-level equivalents such as assembly and the system languages. And then error checking. Here, error checking needs to be done. Many high-level languages enforce a great deal of error checking both at compile time and at runtime. Cost. The ultimate cost of a programming language is a function of many of its characteristics, such as Java. Instead, Java is famous because of its cost, lower cost or no cost. Familiar notation. It should have a familiar notation so it can be understood by most of the programmers. And then quick translation. It should admit quick translation from higher language, from source to relocatable code, and then assembly code, then machine code. Okay. It should admit quick translation. Then efficiency. It should permit the generation of efficient object code. So we can relocate. Modularity. It should the programs can be developed in the language as a collection of separately compiled modules with appropriate mechanism for ensuring self-consistency between these modules. And it should be widely available. There are techniques to be followed to guide for the guidelines of the codes and standards of the codes set by engineering for software engineers. For example, in some companies they are using camel camel naming. Because if I'm saying a variable name such as such as student name, I would say that I want name like that by student name. So here name is a capital letter. So in the middle of the variable, we should use a capital letter such as camel's back. So, and also some companies tested that we can use first letters as capital letters and no letters should be in capital letters like that. It's the guidelines followed by companies, software engineers during development because we will see total quality management and ISO standards and then code review is a code review for a model is carried out after the model is compiled and all the syntax errors have been eliminated. Code review are extremely cost-effective strategy for reduction in coding errors and to produce high-quality code. Normally, two types of reviews are carried out on the code of module. These two are code review techniques and code inspection, code walkthrough. Okay, there is code inspection and then code walkthrough. Two types of techniques. First one, code walkthrough. Code walkthrough is an informal code analysis technique. This technique, after module coded, successfully compiled and errors are eliminated, few members of the development team are given a code few days before the walkthrough meeting to read and understand the code. Each member selects some test cases and simulate the execution code by hand without executing by hand. The main objective of the code walkthrough to discover algorithmic and logical errors in the code. Okay. Even though a code walkthrough is an informal analysis technique, several guidelines have evolved over the years for making this naive but useful analysis technique more effective. Okay. Of course, these guidelines are based on personal experience, common sense, and several objective factors. Okay. Some of the guidelines, like the team performing code walkthrough, should not be either too big or too small. Ideally, should be consist of between 2 to 7 members. Discussion focused on discovery of errors and not to fix the errors. Okay. Then code inspection. The aim of code inspection is to discover common type of errors due to oversight and improper programming. During code inspection, the code is examined for the presence of certain kind of errors in contrast to the hand simulation of coding execution done in code work. Okay. It is more likely that such an error will be discovered with missing semicolons, variable name mismatch, parameter passing, array bounds of array errors. The commonly made errors adherence to coding standards is also checked during inspection. Good software development companies collect statistics regarding different types of errors commonly committed by their engineers and identify the type of errors most frequently committed, such as use of uninitialized variables, jumps into loops, we never use jump inside the loop. Non-terminating loops, incompatible assignments, array index out of bounds, improper storage allocation and deallocation, mismatch between actual and formal parameters, use of incorrect logical operators in or incorrect precedence among the operators, improper modification of loop variables, comparison of equality of floating point variables, and also like typecasting. Typecasting can be also checked. Right? Then clean room testing, pioneered by IBM. Clean room testing, pioneered by, 1 second, please. Okay. Pioneered by IBM. This type of testing relies heavily on walkthroughs, inspection, and formal verification. The programmers are not allowed to test any of their code by executing the code other than doing syntax testing using compiler. The objective of this software is zero defect software. The name clean room was derived from the analogy with semiconductor fabrication units. In these units, defects are avoided by manufacturing an ultra cleaning atmosphere. The clean room approach to software development is based on 5 characteristics: formal specification, incremental development, structured programming, static verification, and then statistical testing of the system. Then software documentation. We in the end we need user manuals. We need to find user manuals, frequently asked questions, many documents. Okay, so for the sake of maintenance to be done. Okay, so there are 2 types here: internal documentation. We will see internal documentation and external documentation, such as adding comments. Okay, so good documents enhance understandability and maintainability of a software product. They reduce the effort and time required for maintenance. Use help document the users effectively using the system. Good documents helps in effectively handling the manpower turnover problem. Even when engineer leaves the organization, a new engineer comes in, he can build up the required knowledge from the documents. Here we have 2 types of documentation: internal documentation and external documentation. In internal documentation, comments such as comments, comment, naming variables, giving meaningful name to functions. Those are considered as internal documentations. Okay, like such as like A is equal to 10, means A made 10, like that. Okay, but even when code is carefully commented, meaningful variable names still are more helpful in understanding piece of code. Then external documentation such as user's manual, SRS document, design document, test document. A systematic software development style ensures that all these documents are produced in an orderly fashion. You can see that documentation is important in IT companies because you can see that it's intangible product. Intangible product. These documents needs to be submitted in time. So they can verify the documents in order to find the percentage of work have been done. Okay. Then testing, important part, testing. We have types of testing here. We will see each one. Some commonly used terms associated with testings are failure, manifestation of an error or defect or a bug. But the presence of error may not necessarily lead to failure. Failure, error failure is different. Error is different. Error is like what we have seen. Like it will give us incorrect result. Failure means it don't even produce any result. That's the difference between error and a failure. You see, error may give you incorrect result. Failure means it don't even produce any result. But error may lead to failure. Okay. Test cases: input, state, output. This is a triplet where I is the input of the system, S is the state of the system, and O is the expected output of the system. Test case and test suite. Set of all test cases of the software product. These are commonly used term we will use here. Aim of testing here, yes. Error-free programs, yes. Error-free programs. Then verification with validation, yes. Verification is the process of determining whether the output of one phase of software development conforms to its previous phase. Okay. Validation is the process of determining whether fully developed system conform to its requirement specification. So what we are doing in validation, we are checking it against SRS document. Okay. Thus, verification concerned with phase containment errors. The validation is about final product. Okay. Then design of test case, how it can be done. Okay. Here we have examples. For example, here we have like we have code for maximum to find maximum value among two values. Here we can take this x, okay, like x is equal to 3, y is equal to 2. Whether this program, this statements is working fine or not. You can say x is equal to 3. Okay, so y is equal to 2. We'll check the condition. Maximum is equal to x. Okay. Next, x is equal to 2, and then y is equal to 3. Yeah, next one. In the same test cases, we have two testing. In the test suite, we have two set test cases. Now x is equal to 2, y is equal to 3. So now it will go to, okay. Here you can see it can detect the error. It's actually y. Okay. Now it can detect errors. Here, the largest test suite here, meaning what we are going to find out is even if the test case is bigger, it cannot find any error. Okay. Now we can able to find the errors with this, but with using this test case. X is equal to 3, y is equal to 2. X is equal to 3, y is equal to 2. It will lead us to find the errors. X is equal to 3. Yes. Okay. Then x is equal to 4, y is equal to 3. Again, it will say 4. Correct. X is equal to 5, y is equal to 1. Again, it will say 5. Correct. But you can see it is producing only x. So there should be here max is equal to y. So this is the correct order of execution. This is the correct programming code. But here you can see by using this test cases, we can able to detect the errors because it produces only x as the result. Okay, you can see in this test case. Okay. in this test case. In the first test case, we can able to find that maximum value for the first test case is true. Another, the exact result produced by this code is again 2. Instead of 3, it produces 2. Because you can see maximum is equal to 0, maximum is equal to x, again maximum is equal to x. So this line should be changed to maximum is equal to y. This is the error we have to find. So even with the correct set of test cases, we can able to find the errors. Even with the large test suite, that doesn't find that there is a possible way to not detecting an error. So there is a need for the guidelines to build test cases. Functional testing, and then structural testing. Okay, functional testing, also called as black box testing. Okay, test cases in functional testing or black box testing are designed using only functional specification of the test software without any knowledge of the internal structure. Black box testing is known as functional testing. In white box testing approach, designing test cases requires thorough understanding of internal structure of the software. Therefore, white box testing is also called structure testing. Black box testing. Here, testing in the large means testing in the small. I mean, unit testing and then integration testing and then system testing. Now we will see unit testing. Unit testing is undertaken after module have been coded reviewed. Okay. Unit testing or module testing is testing the different units or modules of the system in isolation. In order to test a single module, a complete environment is needed. Okay. That is, besides the module is under test itself, the following steps are needs to be in order to able to test the test module. Okay, the procedures. So we are saying that the module is under tested, but we have to find the whole module is working fine. There should be a function call. Data needed from such as global data needed for the module. Okay, function data from other modules. Okay, these are needed. The procedures belonging to other modules that the module under call and the test calls. Non-local data structure, module accesses, a procedure to call the function of the module under test with appropriate parameters. Okay, we have to consider all this to test a single module. Modules are required to provide necessary environment, which either call or call by other modules and under text. Okay, here a stub procedure may produce the expected behavior using simple table lookup mechanism. A driver module contains the non-local data structure accessed by the module under test and would also have the code to call the different functions and define using different parameters. Okay, here you can see the module. We have a single module that is being under test. So there is a need for access to for a need for the module to access global data. So then we can use driver modules. And then there is a need for function calls, either from this module or from called by another modules. Okay, we are testing this module. So this module in return have to send something. So we have to test that too. So stub procedure is needed. Black box testing. Here, there are two main approaches for black box testing: equivalence class portioning, boundary value analysis. In equivalence class partitioning, the domain of input values is partitioned into set of equivalence classes, meaning that this partitioning is done such that behavior of the program is similar for every input data belonging to the same equivalence class. The main idea behind to define the equivalence class is that testing the code with any one value belonging to the equivalence class is good as testing the software with any other value belonging to that equivalence class. We have some guidelines. If input data values to a system can be specified by a range of values, then one invalid and two invalid equivalence classes should be taken. Okay. If input data values can be specified in range of values, one valid, two invalid equivalences. I will say that -2, 0, and then 2000. Okay. -2, 0, 2000. I would say that either true or false, like true or false conditions for this, or minus 20, 12, or 1000 to test the age. Okay, if it is age, there is no one can be minus 20, no one can be 1000. 12 is possible. So one valid and two invalid equivalence classes. Okay, if input data assumes values from set of discrete members of some domain, then one equivalence class for valid input values and another equivalence class for invalid input values. Okay, from some domain. Then, for example, here a software that computes the square root of an integer, which can assume values in the range of 0 to 5000. Okay, 0 to 5000 we can give as an integer value. So therefore, test cases we have in the test cases we have minus 5 invalid, 6000 invalid. So from 0 to 5000 is the range. So we are saying minus 5 and also 6000. So 500 valid. And then boundary value analysis. The boundary value analysis means that error can happen here also in the end, in the beginning or end of the given range. Any type of programming error frequently occurs at boundary of different equivalence classes of input. The reason behind this such errors might purely due to psychological factors. Programmers often fail to see the special processing required by the input values that lie at the boundary of different equivalence of classes. The programmer may improperly use less is equal to less than or is equal to less instead of less than or is equal to, or conversely for greater than for instead of greater than or is equal to. For example, I would say that a student which scores 40, pass mark is 40. Okay, pass mark is 40. So the condition should be like the student is pass if he have marks greater than or is equal to 40. Okay, equal to 40 is also pass mark. So in some cases, if I said only 40, if I write the program as pass, if a student scores 40, then he is pass. Okay, 40 is the pass mark. So like this will condition lead to only 41 is the pass mark. Consider this 40 will be given as fail mark. So that is the boundary value analysis. Okay, for example, this would give the correct result. Then white box testing. In here, white box strategy is said to be stronger. Sorry, one white box strategy is said to be stronger than another strategy if all types of errors detected by the first strategy is also detected by some second strategy. And the second strategy additionally detects some more types of errors. Okay, if we have two strategy, one strategy finding errors, and then second strategy finding the same errors plus more type of errors. Then we say that second strategy is more strong. When when two testing strategies detect errors that are different, at least with respect to some type of error, they are called complementary. Okay, that's an error. First one, we can see that in white box testing, we need implementation data. We are going to check the implementation. Okay, so we need to cover the entire software. Okay, which means that either statement, we have some techniques to cover entire program. First one, statement coverage. Here, the test cases is designed that every statement in a program is executed at least once. Okay, in statement coverage, the test case is designed such that each statement in a program is executed at least once. Okay, the principal idea governing the statement coverage strategy is that unless a statement is executed, it is very hard to determine if an error exists in the statement. There are some unreachable codes also possible. Okay, unreachable codes also possible. Unless a statement is executed, it is very difficult to observe whether it causes failure due to illegal memory access, wrong result computation, and more. Executing some statement at once and observing that it behaves properly for that input value is no guarantee that will behave correctly for all input values. Okay, here we have the program. Greatest government greatest common divisor computation algorithm. Okay, here we have statement coverage. Okay, we need to cover all these statements, right? We need to cover all the statements from here. We have statements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 statements. Now all these statements needs to be executed. Okay. If we choose x is equal to 3, y is equal to 3. First test case. X is equal to 3, y is equal to 3. Int x is equal to 3, y is equal to 3. While x not is equal to y. Yes, it is working. Here x is x 3 not is equal to 3. Yes. No, it is true. Okay, here see 3 not is equal to 3. It means that it will return 3. Okay. Only then if both the values x and y is same, it will return greatest common divisor is 3. Okay, now this statement is covered. And then x is equal to 4, y is equal to 3. Next test case, x is equal to 4, y is equal to 3. X is equal to 4, y is equal to 3. Now, 4 not is equal to 3. Condition is true. Then we entered into the true block. Again, if what we are checking is 4 greater than 3, yes, it is true. Then what we would do is 4 is equal to 4 minus 3. That would say that 1. Okay, x is equal to 1. It will produce 1. Now we have covered 1, 2, 3, 4, 5, 9. Okay, now we need to access these two codes. Now, x is equal to 3, y is equal to 4. Next test case. Okay, x is equal to 3, y is equal to 4. We computed these two codes are not yet examined. Now we need to examine this. So we'll use this x is equal to 3, y is equal to 4 statement, test cases. Now x is equal to 3, y is equal to 4. Again, okay, the condition is true. We'll check 3 greater than 4. No. Then it will go to else block. Now what we do is y is equal to 4 minus 3. So y is equal to 1. It will return 1. You can see now all these statements are executed. Okay. So test cases are important for statement coverages. Then branch coverage. Here in branch coverage based strategy, test cases are designed to make each branch condition to assume true or false value. Branch testing is also known as edge testing. In this scheme, each edge of program's control flow graph is traversed at least once, such as this block. Okay, just this block. You see that, for example, let's say we start here, and we will check while condition 3, statement 3 here, this statement, sorry. What we are checking is, we will check condition 3. If it is true, then we will go to another condition, which is 5. If it is true, then we will execute 6th statement. If it is not true, we will execute 7th statement. Okay. If condition 3 here, if it is false, then we can directly move to 9. We directly move to 9. Okay. So 2, okay. 2, there is no need for 2, it will be split. And then we can go to another one. We have like this. Okay, 1. From 1, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See, we can see by covering this, we have completed all the paths. Okay. For example, if we remove, okay, we can remove this closing points. Okay. Semicolon, sorry, not semicolon, parenthesis, closing parenthesis. We remove closing parenthesis and name only this. we say that 1, 2, 3, 4, 5, 6. Okay, there are 6 statements. Okay, we will start with 1 and then while. Okay, while to be tested. Okay, there's no need for this. From here, we go to second statement. From the second statement, either we can go to third one or fifth one. Okay, third one or fifth one. Okay, if 3 is true, we can execute 4. If 5 is true, we can execute. No, if 5 is true, then no, there is no. Okay. Okay. So even if it is 2 is false, then 4 from 4 to 6. Then if it is false, then again 5 to 6. Even here, if it is false, then we can come to here. So if here, from here, from 2, from while. Okay. So we can see that 1, 2, 3, 4, 5, 6 all have been covered. So what we can do is we are going to cover the branches. Okay. Same by using the same method here. You can see that we can use the same test cases and we can still be able to find errors here. Then conditional coverages. In this structural testing, test cases are designed to make each component of a composite conditional expression to assume both true or false values. In conditional expression, here like this, we can use like A and B or C. Okay, here the components A, B, and C each made to assume both true and false values. Branch testing is probably the simplest condition testing strategy where only the component variables appearing in the different branches statements are made to assume. Thus, condition testing is stronger strategy than branch testing. Branch testing is stronger testing than statement coverage based testing. So, which is the strongest one here? Condition coverage, then branch coverage, then statement coverage. For a composite conditional expression of n components, for condition coverage, 2 power n test cases are required. Thus, for condition coverage, the number of test cases increases exponentially with number of component conditions. Therefore, a condition coverage based technique is practically small if n is small. Okay, if the number of components or number of conditions is small, then it's small. Then control flow graph. Okay, control flow graph. We need to understand the control flow graph. Okay, here the sequence are given for the same program. A is equal to 5, and then next stage. Okay, there is no in sequence. Okay, the programs is executed in the sequence order. Then selection here. If A is B, if A greater than B, then C is equal to 3. Then C is equal to 3. Else C is equal to 5. Then C is equal to C into 3. Okay. It is selection. Then iteration here. While A greater than B, while loop, if it is false, then it will directly lead to C is equal to A plus B. Then if it is true, it will say that B is equal to B minus 1 and B is equal to B into A. Okay. All these statements are covered. Okay. This computation algorithm have given like while, this is the diagram we have already derived. Like we have while loop, okay, while loop 1, okay. Then if X or Y, from while loop, we will do another condition. If, which is 2. If X greater than Y, then there is a divide. If X is greater than Y, then X is equal to X minus 1. Okay, 3. Else, Y is equal to Y minus X. Okay, then return. Yeah, this one. And even from 1 to 6. Here, 6. Just return. Okay. 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 Then we can find cyclomatic complexity. Yes, mutation testing needs for deep. Okay. So that's it for today. I hope